Okay, and welcome to part 2 of our video series about kinetics. And after watching part 1, you should be able to understand what a rate is and how to write a rate for any particular species in an equation. What I'm going to show you here in part 2 is how to write a rate law. And this is from section 2 in Zoomdal, sections 2 and 3. So here's what a rate law is. A rate law shows how the rate of reaction depends on the concentration of only the reactants. So if I have an equation, a generic equation that looks like this, I'm only concerned with the concentration of A and B. It does not matter to me the concentration of C, because if I think about it, C is being produced and it's only A and B that are coming together. So the amounts of those will determine how much C is produced. So when I write my rate law, this is the general form that the rate law takes. So rate is equal to K, which is a constant, times the concentration of reactant A raised to a certain power, times the concentration of B, reactant B raised to a certain power. And it's important to identify what K is. K is a rate constant that is temperature dependent. M and N are reaction orders, and we write them as superscripts, and we say that that the concentration is raised to that power. But what that's really telling us is how important reactants A and B are in the reaction. So I'm going to keep that in mind as I solve for M and N later on. The higher that number, the more important that reactant is to affecting the rate of your reaction. It's also important to know that M is not equal to the coefficient of A, and N is not equal to the coefficient of B. If you keep that straight, we will be in good shape from here on out. So I have an example equation here. I've got ammonium ions reacting with nitrite ions in solution, and they're going to come together to form nitrogen gas and water. So the rate law that I write for that equation is just really simple. I take the concentration of ammonium ions raised to the M power times the concentration of nitrite ions raised to the N power. And that's just the general form for right now. We're not solving anything yet. Here's another example equation that you can write the rate law for. Go ahead and pause it right now and just write the generic rate law for that particular equation. And after you've paused, you should have come up with this for the rate law, that the rate is equal to K, a constant, times the concentration of chlorine raised to the M power times the concentration of trichloromethane raised to a different power. You can pause here, look in your book if you need additional resources, but we're going to move on and calculate M and N, because the rate law can only be determined by experimental evidence. You cannot predict the order from the balanced equation. You need data. And to do this, we are going to use the initial rate. And this is the rate of the reaction at time equals 0. This is the instantaneous rate, right when you put those reactants in your solution. We want the instantaneous rate because we know that most reactions are reversible, but we only are considering the forward reaction right now. So if we take the rate at time 0 when there is no reverse reaction yet, we eliminate that problem and issue altogether. So that's why we use the initial rate, instantaneous rate. So I have a set of data here. I've done an experiment. I've done the equation that I showed earlier. I put ammonium ions in solution, nitrite ions in solution, and they react together. So it looks like I did 3 experiments, and from the first 2 experiments, I held the concentration of ammonium constant, but I changed the concentration of nitrite, and I can see that my rate has changed. From experiments 2 and 3, I can see that I've changed my concentration of ammonium, but I have kept the concentration of nitrite constant, and I can see that that had an effect on the rate. The rate is in reference to the nitrite. So the rate is in reference to how quickly the nitrite ions are getting used up. So you can pause if you need to, write down this data, but we're going to show you how to calculate the reaction orders M and N. So I'm going to compare first experiments 1 and 2. And I'm doing that first because in experiments 1 and 2, I have held ammonium constant, and I've changed the concentration of nitrite. I always have to make sure that I keep one constant and the other one is changing in order to see the effect. So I plug in my rates right here. I plug in my concentrations over here. And then it's pretty easy to see what is going to cancel out. The K's cancel out, and the concentrations of ammonium cancel out. And from here, then, it's pretty simple math. I plug it in my calculator if I need to, but 1/2 is equal to 1/2 raised to an n power. And so if that's the same, then n has to equal 1. So that's first order reaction, we say. To solve for the other reaction order, I'm going to compare experiments 2 and 3. And I plug in my different rates here. I plug in my concentrations for ammonium, which have now changed, but I kept the concentration of nitrite the same. And again, I cancel out what is the same so that I'm only looking at one change. And so if 1/9 equals 1/3 raised to the m power, then m is equal to 2. I plug those numbers in back into my original rate law, and I get something that tells us a more specific picture. It tells me that the concentration of the ammonium is more important than the concentration of nitrite. Like the rate changed more because of the effect, because the concentration of ammonium changed. So that's what that tells us from the rate down there. I can also think about it a little different way, just because I have some simple numbers here. If I look back at my data table, if I compare experiments 1 and 2 again, I am seeing that, again, they're the same, but that I've doubled the concentration of nitrite. When I look at the rate has also doubled. That's just simple mental math that I'm doing right now. If I can tell that changing or doubling the concentration of one reactant doubles my rate, then I can say that it's first order, that n equals 1 for that reactant. I can also do the same thing for the other two experiments, or for experiments 2 and 3. If I can see that from experiments 2 and 3 that my concentration has tripled and nitrite is staying the same, my rate multiplies by a factor of 9. So tripling the concentration of ammonium multiplies my reaction rate by a factor of 9. So 3 times m, or 3 to a power of m, equals 9, so m is equal to 2, like it's squaring it. And I get the same orders that way. This is kind of a shortcut, and this really only works well if you have simple numbers that you're working with. Otherwise, the method that I showed you on the previous slide will absolutely work, because then you can see, you can plug in more numbers if you need to. But this is just kind of a shortcut for if you've got simple numbers. At this point, I can now solve for K, the reaction constant. And to do that, I can just pick any set of data from any of the experiments. Here I picked the data from experiment 1, and I plug in my numbers. I make sure now to take into effect the reaction orders that are these superscripts. And when I rearrange and solve for K, I get 0.060 for a value of K. And then if I put that into my rate law again, and now I have an actual value for K. So here's another practice problem, just a generic equation. Doesn't matter what A, B, C, and D are, but you've got some data below. And so go ahead and pause right here and answer these two questions. You are going to find the rate equation for the reaction, but now you are going to solve for the reaction orders, and then you're going to solve for the numerical value of K. You also need to kind of follow the units here with K. It can get a little tricky, but follow through with what units are canceling. Go ahead and pause and do that calculation. So after we've paused, this is our solution. We've got K is equal to the concentration of A squared to the concentration of B to the first power. Solving for K for any particular experiment, I get this for a value and that for my particular units. So remember that you can rewind this and pause it at any time if you need to go back and review those examples again. But now you should be ready to do Lesson 1 from Chapter 12. In Lesson 1, the page numbers and the problem numbers are on here, and that is calculating rate laws like we just showed you here in this video. Please come prepared with those on Monday. Thanks for watching, and we hope you have a great weekend, and we'll see you back here on Monday. All right, bye guys.